Good afternoon, everyone. I'm Clem. I do my PhD under supervision of Yuri van Deuven at Anton Pannekoek Institute for Astronomy, which is located at the University of Amsterdam, and also at ASTRON, which is the Netherlands Institute for Radio Astronomy. Today, I would like to give an update on the collaborated multi-frequency radio and optical observations of the specific radio pulsar binary, J1614-2318. I'll outline 13 years of observation of this binary, dive more into the pulse profile studies, and then show what we currently think about the binary evolution. To begin with, there are different classes of spinning neutron stars or pulsars with different spin periods and spin downs. These different classes are normally represented on the standard P-Pdot diagram that further separates them in terms of characteristic age, magnetic field strength, or spin down energy. We see that, for instance, long period normal pulses appear next to the center of the diagram, and then they move downwards due to the spin down and magnetic field decay until they reach the so-called death line, so that they cease their radio emission. On the lower left end of the diagram, we see short period millisecond pulses that are normally found in binary systems, and they can spin up due to the accretion and gaining the matter or angular momentum from their binary companions. They are normally old pulsars with moderate magnetic fields of 10 to the 8, 10 to the 9 Gauss, because the accretion causes the decay of magnetic field. There are also rotating radio transients that appear next to normal pulses, but they are generally brighter, and they emit only sporadically, so that they are normally found via single pulse searches and not periodic searches. And on the other extreme, there are also magnetars on top of this diagram that have very strong magnetic fields of 10 to the 14, 10 to the 15 Gauss, so that their radiation is caused by the magnetic field decay. We'll hear more about these objects later today. I'll focus more on millisecond pulsars. As I said, millisecond pulsars, they are bind in binary systems with their companions, such that they undergo a period of matter transfer from them. They're normally found in globular clusters, such that the crowded environment in this cluster can help them gain their companion more easily. But on the other hand, the strong gravitational potential of the globular cluster doesn't normally allow us to measure the intrinsic pulsar spin down and therefore its magnetic field. Nowadays, there are more than 350 millisecond pulsars known, and the fastest millisecond pulsars, they can span up to the point when their spin down energy can be similar to the young pulsars, and therefore allow them to emit also in gamma ray. And therefore, these millisecond pulses can be also radio counterparts to the unidentified gamma ray sources. For instance, those found with the EGRET telescope on Compton Gamma Ray Observatory. And one of them was the radio pulsar J1614, which was unexpectedly found via the Parkes survey of 56 mid-latitude EGRET gamma ray error boxes by unexpectedly, I'll come to this point later, but this survey was made at L-band at 1.4 gigahertz and used the single 4-pointing tessellation pattern that covered 95% confidence region of each of the EGRET error box. It covered also in total 140 square degrees of the sky at moderate galactic scales about above 5 degrees. After the discovery, there was a follow-up with multiple different telescopes, such as Parkes telescope, Green Bank, Westerbork, and also low frequency rate. They spanned for almost 13 years and covered a huge frequency range from 150 megahertz up to 2 gigahertz. There were also timing observations made on a roughly monthly basis for Green Bank and Westerbork, and they ended up in sufficient amount of times of arrival, TOAs, for a timing solution. Here are the pulse profiles. They were made at different frequencies from different telescopes. The procedure of making these pulses is standard. We apply fast Fourier transform to the recorded dispersed data and then stack every single pulse on top of each other to get the highest signal to noise. We see that the profiles get more noisy towards the higher frequencies, whereas at lower frequencies there is a more detailed structure shown. And what's more interesting for low frequency profiles, especially for 350 megahertz GBT and Westerbork profiles, we see that there are additional wings next to the main pulse, therefore increasing the pulse width to almost 60–90%. And this can also imply the presence of conglomerated conal emissions, so that different beam components, I'll come to this point later. But first, in particular for Westerbork observations, we see that at different bands, at L band, 1.4 gigahertz, the pulse profile is much more dim, which results in almost 3 times less signal-to-noise ratio to that of B band, 350 megahertz, given 2 times broader bandwidth, but 3 times shorter observation time. And this can mean that the spectral index and the spectral law is steep, so that we should expect a higher flux density at lower frequencies, which was one of the key points to try and observe this pulse at even lower frequencies with the LOFAR. A few words about polarization studies. In general, polarization can get a feeling of a Faraday rotation and interstellar scattering from the interstellar medium that the pulsar beam has to travel through in order to be captured by the radio telescope. It can also give a better estimate on the binary system angle, that is the angle between magnetic axis and rotation axis. Therefore, later observations with all these telescopes were made in full Stokes regime to try and obtain polarization profile of the pulsar. Even though past Parkes and GBT observations didn't really made a success in getting the polarization due to the technical difficulties, with Westerbork we were able to sum 15 hours of observation at 350 megahertz and get 90 sigma signal-to-noise ratio. However, the polarization was quite monotonic, around 0 flux, and thus we think that the pulsar should be really weakly polarized. Again, as I said, since most pulsars have steeper spectra and they have higher flux densities towards lower frequencies, they normally peak at around 150 megahertz, which is the central frequency of LOFAR high band antennas. That's why we tried to observe this with LOFAR. We did 3 2-hour observational sessions with around 100 megahertz bandwidth and 150 microsecond sampling time. We will not be able to detect LOFAR, the pulsar with LOFAR, but set the limit on the sensitivity to about 0.1 millijanskis. Possible reasons for the non-detection can be extremely low declination for this pulsar according to the LOFAR, the angle, but also this can be pulsars intrinsically low brightness. And the scattering was estimated to give only 5% for the pulse broadening. Back to the beam components, as I said, since low frequency profiles have additional wings next to the main pulse, we think that there might be 2 different beam components present for this pulsar, which correspond to a different region of the pulsar magnetosphere, and they depend on the observational frequency. Normally, they are described by the pulse width, normally 10% and 50% level of the main peak of the pulse. That is this width. So what we did, we tried to see whether this pulsar appears on the width towards the period relation. We also used known measured pulse width from other pulsars with the separated known beam components. We estimated errors from the low frequency profiles for our pulsar. We also used the low boundary line. That basically means that there shouldn't be any pulse profile structure resolved below this line. And we consider the pulse width ratio because both widths strongly depend on the observational frequency that scaled them in the same manner. And that's why for the ratio, it
shouldn't be much of the dependence. And we see that our pulsar also appears above this low boundary line that is consistent with these predictions, which means that both, this holds not only for core components, but also for conal components, exactly in the same manner, which means that these both components can indeed be present for our pulsar. Now, to further study, to better determine the binary parameters, we also observe the position of the pulsar in optical with the 4.1 meter aperture 1000 astrophysical research telescope at airband. We did 15 exposures of 1 minute with a 0.8 arcsecond scene. We didn't see the counterpart down to 25th magnitude 5 sigma significance, which is pretty deep. We also estimate the extinction, which is not really significant, it's below 0.5 magnitude, and shouldn't really affect the non-detection of the counterpart. And because there was an absence of a counterpart in the solar field of view, we think that this might imply that the companion is old and called helium white dwarf star, which is also consistent with the evolutionary models of helium white dwarf and also with the other known pulsar binaries with the helium white dwarf companions. Here's the timing solution. We obtain times of arrivals from all but LOFAR observations. Then we combine all of them and feed for pulsar position and binary motion. The timing parameters are inconsistent with the discovery paper. And from the pulsar ephemeris, we found the eccentricity to be around 0, which means almost circular orbit. We couldn't determine the binary motion. It was not really significant in our measurements. And also, we couldn't measure the Shapiro delay, which might mean that the orbit is more at the lower inclination or towards the face-on position. So for the properties of the pulsar, the pulse period is quite long, it's at around 30 milliseconds. The spin down is typical for millisecond pulsars. The characteristic age is around 10 gigayears, which is also typical. The orbital period is 3 days, and dispersion measure is around 50 parsecs per cubic centimeter, which applies 2 or 3 kiloparsecs according to different electron density model. This is the position of the pulsar on a P-Pdot diagram. We see that the pulsar stands a bit aside from the main bulk of the MSP population, and that is possible because of the extended pulse period. The magnetic field is also quite typical and consistent with the pure dipole radiation for the MSP population. At the same time, it also means that the companion was not really able to fully recycle the pulsar. The spin down energy is quite low, and therefore is not sufficient for the pulsar to emit in a gamma ray. And this is indeed the reason why the pulsar was found unexpectedly. So it's not associated with any of egret sources. And what's more interesting, the minimum companion mass is really small compared to the pulsar spin period, which makes this the second lowest minimum companion mass for partially recycled pulsars with the spin periods between 10 and 100 milliseconds. The record holder, the first smallest minimum companion mass belongs to the similar pulsar binary that was found during the high time resolution survey with Parkes. It has also similar pulse period, very small minimum companion mass, and also other characteristics which is pretty similar to our binary. And that implies that for these both pulsars, there might be a different evolutionary scenario of the binary. And speaking of binary evolution scenarios, here we plot the dependence of a binary orbital period versus the medium companion mass at a 60 degrees inclination. We also show the theoretical correlation between these two parameters given different progenitor metallicities. And we also put other pulsar binaries with well-measured masses, and our pulsar is shown here. The spin period is shown in parentheses. And if we apply error bars on the mass given Shapiro delay measurements, and for those that don't have these measurements, we apply uniform distribution of orbital orientations, then these error bars can also move forward and therefore fit this theoretical relation, which means that
in this case, the orbital inclination can be really small, and the companion mass can be indeed more heavier. But in this case, then it's the randomly oriented orbit is very unlikely. It's only 8% probability of getting this rare inclination. However, in this case, there is almost no influence on the pulsar from a companion, such as eclipses, and therefore the only estimate we can get for the mass is from Kepler laws. And this can explain why the mass of the companion is so underestimated. We are unable to measure Shapiro delay and therefore not able to measure post-Keplerian parameters, such that leads to direct estimated masses. In this case, one more puzzle is why there is a relatively long spin period, because if the pulsar binary undergoes a period of mass accretion, what can also be is that the magnetic field should inhibit the process of accretion so that the pulsar cannot be easily spun up. Therefore, we think that there might be an inefficient accretion onto the pulsar such that the magnetic field can be initially weak and then still ends up to be normal, typical for pulsars as 10 to the 9 Gauss. However, the accretion channel may be relatively weak such that the pulsar is not really spun up because of that. Other possible scenarios can be that there might be different formation scenario. For instance, as if the oxygen neomagnesium white dwarf can turn into the neutron star under the accretion-induced collapse. However, this applies only when the orbital period of the binary is really long and from 10 to 60 days, which is not the case. That's why we think it's not really a plausible scenario for our case. And also there can be both different mass and composition of the binary, such that with the carbon helium white dwarfs, we know that many pulsars with such type of companions can be partially recycled. In this case, the mass should be lower, the mass should be higher, and the evolutionary scenario can be completely different from those I showed earlier. To sum up, this is an overview of the 13-year campaign of radio observation and timing of this particular binary. We saw that the spin energy is not high enough to produce gamma ray emission. That's why the pulsar was found unexpectedly. We saw additional wings that results in an increase of pulse duty cycle, which means the presence of additional beam components, and also that the evidence that we have almost 90% coverage of radio beam means that the magnetic axis can be nearly aligned with the rotational axis. And at the same time, if the companion mass is heavier and the orbit is at low inclination and face on, then the orbital line can also be nearly aligned with the magnetic axis and rotational axis. That's why we have 3 nearly aligned lines, and therefore we might deal with the rare case of a nearly aligned rotator. And of course, the discovery of more such alike pulse binaries can shed more light on evolution of such binaries, as well as accretion efficiency of these binaries. Thank you.
Thank you very much, Klim. Are there questions? Dick?
So, can you really rule out a more massive companion? At this 0.022 number, is that the sort of the mean or the median value that you expect? If you've got a almost aligned system, almost face-on system,
yep.
Could the companion mass be much larger?
Yeah, I think because we can't really constrain the mass because of the face-on orbit. The mass can be heavier, and we also saw from the evolutionary scenario that if it can fit the theoretical prediction, then it should be heavier.
But you don't think a double neutron star system is possible?
But then it should be much heavier.
That might be
it's not prohibited. So yeah.
Are there more questions? If not, let's then thank the speaker again.